Hello, this is Amin Sheikh, and this is my Lab 4. So the purpose of this lab is to use real and simulated circuit equipment to complete several measurements with basic circuits. These circuits include an RC circuit and a resistor circuit. The results are measuring current, potential difference, and the graph of potential difference, as well as charge time, discharge time, and the effects of a light bulb with an RC circuit. So some key fundamentals are Kirchhoff's loop rule, Ohm's law, and the junction law. Kirchhoff's loop rule states that the sum of all voltage drops in a closed circuit equals 0. Ohm's law is V equals IR, which is voltage equals current times resistance. And the junction law states that the total current entering a junction is equal to the current leaving. So looking at the resistor circuit as seen to the right above and the circuit model as seen to the right below, some major questions are what are the currents I1 and I2? Well, as read from the ammeter, it was 20 milliamps, and by using Ohm's law, we're able to do that 3 volts divided by 147 ohms is equal to around 20 milliamps. What happens if we reverse the ammeter? Physically, the signs change, but on the simulator, there is no change. In replacing the ammeter measuring I1 with a voltmeter, what happens? Well, the voltmeter will read negative 3 volts because the voltmeter internal resistance is very high, so practically all the voltage drop happens there. While with the ammeter, the reading will just be 0 amps because due to the high internal resistance, the circuit essentially acts open. So some more major questions are what are the potential differences around the circuit? I calculated them and you can see them here, but what's interesting is that the currents at all these locations remains 20 milliamps and the summation of all these potential differences is 0 volts because we have to obey Kirchhoff's loop rule. So why doesn't the ammeter change when the voltmeter is attached? Well, the voltmeter may allow some small current flow, but the junction rule ensures that the current remains 20 milliamps before reaching the ammeter. So what happens if we place the ammeter in parallel with the 100 ohm resistor? Well, the current will jump to 60 milliamps because the ammeter has less resistance than the 100 ohm resistor, thus reducing the total resistance. So what is the resistance of the components based on the calculated V and I? Well, for the 47 ohm resistor, I was able to calculate 48 ohms, and for the 100 ohm resistor, I was able to calculate 102 ohms, and then for the wire and ammeter, I got 0 ohms. Now talking about the RC circuit, some important questions are what happens to the light as the capacitor charges? Well, the light appears bright at first, but fades away. This is similar to what happens when you connect the capacitor to the bulb. As the capacitor in the circuit charges, what happens to the current? Well, the current starts off at the maximum value and then approaches 0. This is the same thing that happens when the capacitor discharges, and the time it takes to charge and discharge the 100 ohm bulb is the same. It's 9 seconds. And for a 20 ohm bulb, it's double that time at around 19 seconds. And so in a simulated scenario, we had a 9 volt battery, 30 ohm bulb, and 200 millifarad capacitor with a calculated RC of 6. We did the simulation and then graphed the data and plotted the natural log of the change in V over the change in 0 and the slope, which is equal to negative 1 over RC times time. Well, negative 1 over RC is the slope, and the slope was negative 0.1634, so thus the graph RC is 6.1, which means the graph value of RC is very similar to the calculated RC. Nice. So some sources of error is just human error and imperfect physical equipment that might slightly alter our measurements. So some potential questions are, what if we use an actual ammeter? Well, flipping the leads of a physical ammeter causes a sign change, and secondly, this physical ammeter likely has a small resistance, thus affecting the current slightly. Also, what if we use a real battery to charge the capacitor without a resistor? Well, in the simulated model, it assumes no resistance from the wire, so the capacitor charges instantly. Well, in real life, wires and batteries have a slight resistance, so it would not be an instantaneous charge. It would take a slight amount of time. Thank you for listening.